So thank you again. We are going to begin. So as I told you earlier that we are going to begin with a implementation of a simple implementation of a Newton-Raphson method in MATLAB. So we'll to do this, we'll do using an example. So we'll mainly use Newton-Raphson to find a root of a real valued function. So we are going to have a sample function which we are going to solve or to find root using Newton-Raphson method. So in MATLAB we begin by clearing the to clear the command window. So we also clear the variables from the workspace. So we write clear. We can also close any other open figure or any other open MATLAB, so we can use close all. So then we can start by defining our function. So we define our function. So a function, let's say, take for example, I have an example of a function. So if you want to define a function with a variable, with an independent variable x, so we can use that method x. So we can use a function like the one here, 0.5 times x. So we are using x as our variable, so and we indicate that every x will be cubed, then minus 4 times x. So this is a function that I once did for a client, squared plus 5.5. so this is just an example. You can use any other example or any other function example. So here is our function, so we can use that to close. Then for the formula for the Newton-Raphson, so we need to know the formula that we use for the Newton-Raphson, and I have the formula here. So this is the formula. That is a method we are going to implement. As you can see, we have x naught, which is our x variable. So as you can see, we have our x1 and we have our x naught. So for us to find our x1, we need to use the previous x, and the previous x is the one that we are defining as x naught. And as we can see, we are minusing the evaluation of the function at the previous x, and the evaluation of the derivative of the function at the previous x naught. So once we loop through the formula, we are able to determine the value x1, which will give us the root of the function, So using this formula, we have already defined our function. As we can see, the function f. So we now need to find the derivative of this function. We need to find the derivative of that function so that we can get the denominator that we have in our formula, which is the f apostrophe. So we now need to find the derivative. So to find the derivative, you can use df dx. So we then state that of course we are using, again, it will have an x as the variable. So I can copy that x. Then I need to do the derivative. If I do the derivative, you already know how we do the derivative, I'm assuming. So we have something like that. then 8 times x to power 1, we don't need to write to power 1, then plus 5.5. So something else that we need is somewhere to start. We need somewhere to start. As we can see in the formula, there is this x0 for us to get x1. So at first we need to have an x0, which will be our initial guess, so that we can have somewhere to start. So in that case, we need to define our initial guess. So initial guess. So our initial guess, in this case, I have used x0 equal to 1.4. So one way you can use to determine the initial guess, you can plot the function. If you plot the function, you will see the point at which you expect your root to be. So at that point, you can get your root should be very near to 1.4. So that's why I'm using 1.4 as my. That's why I'm using 1.4 as my initial guess. So another thing that we need is for us to make our loop, for us to make our iterating loop, we need to know the amount of accuracy that we want to achieve using our method. So in this case, we can use our tolerance, or the amount of accuracy that we want to achieve as. So let me define my tolerance as tol is equal to 1 exponent minus 10. So that's the accuracy that I want to achieve. So my approximate error should be less than that. I also need to have an estimated number of iterations. So I can state my n equal to 100. Then another thing I need now to evaluate. My function. I need to evaluate my function at the initial guess, or at the initial x. So my function at the initial x, let me call it a value. So my function at the initial guess will be equal to f is equal to x0, because I already have this, my initial guess as this. So I can use that. So I have evaluated my function already. So then in this case, I want to use a while loop. So I also need to initialize. I also need to initialize the number of the iterations. So my iteration will start at iteration equal to 0. So I also need to initialize my error. I'm taking it to start at 100. So of course we expect an error less than 100. So this is just somewhere that we want to start at. So then we start now writing our formula. Before we write our formula, we would like to determine the number of iterations. So we can state n iterations, the number of iterations. So we initialize equal to 0. So again we can state that our x at the beginning will be equal to the x0 that we have here, the x0 that we have here. So we can again add it there. So now we want to use our while loop. Of course we know how while loop works. So we start with while. So we are checking whenever that our error So we can we started by defining our initial value of error. Whenever that our error is less than or is greater than, because we wanted to come to less than tolerance, whenever that our error is greater than tolerance. Add, because now we want to check the two conditions. We want to check the conditions of when the error is greater than the tolerance and when the iterations are less than, when the iterations are less than, as long as iterations are less than the initialized iterations. I hope you get it. So that this, now we want to implement our formula within the loop, this formula within the loop. So we say that for us to determine the formula, we need to start with x. The x is the value that we are finding. X is the value that we are looking for. So x will be given by x, which will be the previous x. The x after the, on the right side of the equal sign is the x, that we have determined in the first iteration or in the previous iteration. So minus, we evaluate the function at the previous so like I've said, we evaluate the function at the previous x, then divided by, we evaluate the derivative. We evaluate the derivative, which we name df dx at the previous x. So as you can see, the formula, I have implemented that formula here. So again, we also need to determine the approximate error. We want to determine the approximate error, which we are using in the determining whether we have to terminate the iterations. So for us to be able to evaluate the error, we need to hold an x. So before we evaluate for an x, we need to have an x here, x hold equal to x, and x, the previous x. We need to have the previous x. So once we have the previous x, now we can use that to find the error. So we can state error is given by abs. So absolute, we are removing the negatives and the positives and showing our value is absolute value. So we take x, now our current x, which we have evaluated here. We take our current x, you minus the x hold that we had evaluated in the previous iteration, then we divide by the x, the current x, which is more accurate. Then we can multiply this by 100. We can multiply this by 100. So this gives us the, all this time you're closing to ensure that you don't display everything on the command window. So this one gives us approximate error. That gives us approximate error. So once we have now found that, we need again to find the sum of the iterations, so that at the end we'll know the number of iterations that we have used to achieve the final value of the root. So iteration plus 1. So in every iteration we are adding 1 to the initialized variable for iteration. So then we now need to add our while loop. And finally we will have, at the end of the while loop, we'll now have our solution we now have our solution, which is the root of the function which we have here. The root of the function which we have here will be given by x. Then we can stop closing that so that we can duplicate on the command window. Then eventually we have the number of iterations. So we can write it like that. So the number of iterations will be equal to what we have here. So we can copy it here. So that's how we evaluate. Now let's run our code. So we are running. We have already saved our file. Let's run our code and see. So we have run our code, and here is what we get. So you can see that we have obtained our solution, which is 1.4798, and the number of iterations that we have used to achieve that solution is 5 iterations. So that's how we implement the Raphson method. Thank you.